Hello, this is Chapter 5, Timber Design. In this slide, I will limit the topic to timber column. And this is part 2 under Chapter 5. Introduction. This slide shows a structural component subjected only to tension or compression, such as columns, vertical wall studs, truss, and bracing element. This is post or columns which receive compression loads. Meanwhile, this is the truss, where in truss system there is tension and compression members, and this is the bracing element. Okay, so this is the bracing. The support bracing, and here the vertical element here is the cord. Okay, so this is the bracing, and all these structural components is subjected only to tension or compression load. Design of compression member. So in this topic, the subtopic part 2, chapter 5, we will focus on column design. Before we go further to the column design, we need to consider some design consideration, where the first part under the design consideration is the main consideration. So compression members are commonly used as column in building structure, cords or web in truss, okay, bridge, piers or braces in frame structure. Okay, the maximum strength of compression members depends on a large extent on the member length and support condition. Thus, we need to consider the slenderness ratio, the effective length, when designing the compression member. So first, let's look at slenderness ratio. Slenderness ratio relates to positional restraint of ends, lateral restraint along the length, and cross-sectional dimension of the member. And this slenderness ratio indicates the susceptibility of the column to buckling. So this is, for example, this is a column subjected to loading P, and this column at certain value of load will starts to buckle, okay? It starts to buckle, and this buckling depends on the column length. Either it is slenderness or long column or short column. And this slenderness ratio, the formula is derived from the Euler Formula. So columns with lower slenderness ratio are classified as intermediate and are analyzed with the Johnson formula. But however, in this syllabus, we focus on the slenderness ratio based on Euler Formula. So this is Euler Formula. Formula for slenderness ratio is lambda equal to L effective divided by radius of gyration. Where this radius of gyration is equal to this formula. Okay, so I is the moment of inertia divided by area of column. And this L effective can be determined from clause 12.3 effective length. So under this clause 12.3 Malaysian Standard 544, there is table 9 in page 27. And this table shows for the this table represent the particular ends condition. And also effective length based on this standard can be derived also from the deflection form of compression members affected by any restraint and or fixing moments. So the effective length is considered as the distance between adjacent points of zero bending moment which the member is in single curvature. And in this course, we will derive the effective length to calculate the slenderness ratio based on table 9. So let's look at table 9. So this table is extracted from Malaysia Standard 544 Part 2 2001, clause 12.3. So there are 5 end conditions for column. So the first one is column is restrained at both ends in position and in direction. Okay, so this is case for end condition number 1. So here both ends, this is the column, and both end column is restrained at ends position and also direction. So it is fixed in position and also direction. So this is the first case. So for the first case, we need to multiply the L with the 0.7 to get the effective length. So next is the restraint at both ends in position and one ends in direction. So this is the second end condition. So this is the straight column. Okay, so one end is restrained at both ends in position and one ends in direction. So this is pin, here is pin, the top end is pin, meanwhile the bottom end is fixed. So fixed meaning it cannot move in any direction. Meanwhile for the pin, for the pin ends, pin support, so it can move in one direction. So this is end condition number 2, where you need to multiply the L with 0.85 to get the L effective. So the third end condition is restrained at both ends in position but not in direction. So this is the third case. So both ends is pin. So pin, where pin meanings the end of this column, okay, is restrained in position. It cannot move in position, but it can move in direction. Okay. So for the end condition number 3, you need to multiply the length with 1.0 to get the L effective, the effective length. Okay, so next end condition is number 4. So this is case number 4. Okay, so restraint at one end in position and in direction, and at the other end is direction but not in position. So this is the column. One end is fixed. So another end is roller. So this end, bottom end, okay, this is restrained in position and in direction. So meanwhile for this end, it is restrained in direction but not in position. Okay, so when end condition number 4, so we need to multiply the L with 1.5 to get effective length for end condition case 4. So next, the last one is end condition number 5, where the end condition restrained at one end in position and in direction and free at the other end. So this is case number 5. So we have, this is straight line, okay, the column. Okay, so this one end is restrained at in position and also in direction, meaning this is fixed. Okay, fixed end. Fixed support, we want at this end, each is free. Each is free, thus we need to multiply L with 2.0 to get the effective length. So this is the actual length. This actual length is this value. And this is the length. I'm sorry, please assume this is the straight line. Okay, so this is the length. So let's look at this diagram. So this diagram represents each end condition as stated in table 9. So the first one, the L effective is calculated using 0.7 L, where this L is the actual length. So this is the actual length. The L for column, and LE is based because here is the fixed end condition. So this is case number 1. So restraint at both ends. So both ends is restrained in position and in direction. So the buckling, so here it starts 0, 0. So because here is restraint support, so it starts 0, so it starts to buckling start at certain distance here. So same goes here, 0, then it starts to buckle. So this is from this point into this point, this is called the L effective. And this length is measured by using 0.7 L. Okay, so this is how we measure the length for column. So under the column design, we need to consider the L effective, okay, based on due to the Azure and the bending. Okay, the bending. So the second case is 0.85, restraint at both ends. Sorry, restraint at both ends in position. So both is restrained, but one end is restrained in direction. Okay, so here is pin, here is fixed. So the buckling shape is like this. Okay, so here start is 0. So after certain length, it starts to buckling. Okay, so this is our L effective from here to this point. So this is the L effective. So for this case, L effective is calculated using 0.85 L. So next is the restraint at both ends. Both is restrained here, but not in direction. So it can easily move in horizontal direction. Okay. All right. So our buckling shape is for the pin column, pin support. So this here is pin support. So the buckling starts. So this is the L effective. The actual length starts from this point. So and buckling starts from here to here. So meaning the L effective equal to L. Okay, so this is for restraint at both ends in position but not in direction. Okay, so next is the case for the restraint at one end in position. This is restraint at one end in position and direction, meaning this is the fixed support. And at the other end, this is another end, is fixed in direction but not in position. Okay, so this is the buckling shape for the case 4, where we need to multiply the L, the actual length, with the 1.5, okay, to get the L effective. So this is the buckling shape. Okay, so our L effective from this point, okay, so it extends to a certain length, okay, and this length, the L effective, is equal to L multiplied with 1.5. Okay, so because at this end, each is not fixed in, not restrained in position. So the L effective is actual length multiplied with 1.5. And this is the last end condition where it is restrained at one end, okay, no rotation at this end, both in position and also direction. Meanwhile, at this end is free. Okay, so this is the shape of the, so this is straight line. Okay, so 0 at certain age. So this is the shape of the buckling. So the L effective is 2 multiplied with actual length. And all this buckling is due to the compression load. Okay, so this is the axial load, the compression. So next, we look at the radius of gyration. So radius of gyration is square root of moment of inertia divided by area of column. So we multiply this, we substitute this value, the I of gyration, into this slenderness ratio, and L effective divided by I, the slenderness ratio, we can get this value. So the slenderness ratio is represented using this symbol, the lambda. So lambda equal to L effective divided by radius of gyration, and this radius of gyration is calculated using the square root of moment of inertia, where our moment of inertia is B h power of 3 divided by 12, and I divided by area of, cross-sectional area of the column. And we also can simplify the I of gyration equal to B divided by square root of 12, where B is the least lateral dimension, so the smaller dimension for the cross-sectional. Okay, so let's say for this case, this is the B. So for if this is the cross-sectional, so here is the B. So please take note that the B is the least lateral dimension. And this calculated slenderness ratio should not exceed the value of 180 and also 250 based on clause 12.4 Malaysian Standard 544. So first let's look at this condition. So slenderness ratio should not exceed than 180 for any compression members carrying dead and imposed load other than load resulting from wind, and second, any compression member however loaded which by its deformation will adversely affect the stress in another member carrying dead and imposed load other than wind. So this is for the first condition, where the slenderness ratio should not exceed 180 under this condition. Okay, so the second situation is the slenderness ratio should not exceed 250 for any members normally subjected to tension or combined and bending arising from GK, the dead load, and also QK, the imposed load, but subjected to a reversely of axial stress slowly from the effective of weight, and any compression members carrying self-weight and wind loads only. So in our syllabus, since there is no wind load, so we refer to 180. Okay, so for the less than 180, there is no wind load. Meanwhile, for the less than 250, there is wind loads to be considered. Next is the modification factor. Okay, before we go further to the modification factor for column design, we refresh back the design for beam. So in beam design, timber for beam design, we have seen the K1. This K1 is the load sharing system. K2 is the length and position of bearing. The K1 is the duration of loading. Okay, duration of loading. Okay, K2 is the load sharing system. K3 is the length and position of bearing. K4 is the form factor. K6 is the depth factor. Okay, so you will use some of these modification factor in designing compression members. And in this part 2, you will be introduced with K8. Okay, so this K8 can be found in clause 12.5 Malaysian Standard 544 in page 27. So there are two methods to determine K8. The first one is by using equation. So this is the first method. So this equation in Malaysian Standard 544 can be found in page 58 under Appendix D, Modification Factor for Compression Members. So this is Appendix D in Malaysia Standard 544 Part 2, 2001. So in this equation, this is the stress C represent the compression permissible stress, okay, for the compression. So this is stress C. C represent compression. So equation for this permissible stress is compression parallel to grain, okay, multiply with K1. So this is the K1. This K1 is similar with the beam design, and this stress is determined from table 1, 2, or 4. So table 1 and 2 is based on the species name. Meanwhile, for table 4 is referring to the strength group. Okay, next is the modulus of elasticity. So in this K8, we use the E minimum, and this E minimum is determined from the same table as in compression parallel to grain. So this is compression, this is parallel to grain. So next is the slenderness ratio. So this is the slenderness ratio. Okay, you have seen this in the previous slide. And here is the eccentricity factor taken by 0.005 multiply with slenderness ratio from this equation. Okay, and N is the reduction factor used to derive grade compression, stresses, and moduli elastic. And in this case, we take N, this N, equal to 1.5. So this is the formula to calculate K8. So the second method to determine K8 by using table 10. So this table 10 in Malaysia Standard 544 can be found in page 29, and this is table 10 modification factor K8 for compression member, okay, from from Malaysia Standard 544 Part 2, 2001. So we extract some of this table into slide as you seen here. So this is some part of the table 10. So where we can see there is a column here. This is the first column. So this first column is modulus of elasticity divided by compression parallel to grain stress. Okay, so this value, this E, and also compression parallel to grain stress is determined from table 1, table 2, or table 4, similar with beam design. So next is in this row, meanwhile in this column, in this big column, okay, there is the second row. In the second row, we can see the slenderness ratio. So slenderness ratio again is equal to L effective divided by radius of gyration, and this L effective depends on the end condition, and also this radius gyration is equal to square root of I divided by A. Okay, So when after you calculate this radius of gyration, we can get this value. Okay. And also for the rectangular section only, you can also determine the value K based on L effective divided by B. Okay, the least dimension. Okay, so this is second method to determine the modification factor. So first you need to calculate this value. Okay, next you need to calculate this value, and then you match it inside here. Let's say 600 for this value, and let's say for the slenderness ratio is equal to 40. Thus your K8 is equal to 0.774. In case where the value for both this and the slenderness ratio not stated in this table, let's say it is 650 and also 35, so you need, in this case, you need to calculate based on interpolation. Okay, do the interpolation. And next is the design process. So this is the design process for column compression member. So there are two cases. Okay. So the first one is member subjected to axial compression only. So this is the first case. Okay, member subjected to axial compression only. And the second case is member subjected to axial compression and also bending. Okay, so there are two situations need to be considered when designing a timber column. So the first case is member subjected to axial compression only. The second case is axial compression, member subjected to axial compression and bending. Combination of axial compression and bending. First, let's look at case number 1, where member subjected to axial compression only. So, member subjected to axial compression only is referred to clause 12.5 Malaysian Standard Part 2 2001 in page 28. Okay, so you can find this clause at page 28, okay, in Malaysian Standard. So under this checking, we need to ensure that, or to verify that this applied compressive strength is less or equal to permissible axial compressive strength. Okay, so where our axial compressive strength is calculated using this formula, the axial compressive load divided by cross-sectional area. So this is the column, and this column is subjected to P load, and this P load is the axial compressive load, compression load. Okay, so axial compression load. So meanwhile, A is the cross-sectional of the column. Okay, so this is the cross-sectional of column. Okay, B, H or D. Okay, so next, this permissible compressive stress, okay, is calculated from this equation. So the selection of this equation is based on this slenderness ratio. Okay, so for the slenderness ratio, the first condition where the slenderness ratio is less than 5, then we use this equation to determine the permissible compressive stress, where this compression parallel to grain is determined from table 1, 2, or 4. Okay, so then here is the K1. K1 is the duration of loading, and here is the K2, and this K2 is the load sharing system. Meanwhile, if the slenderness ratio more than 5 or equal to 5, so the permissible compressive stress is calculated using the compression parallel to grain from table 1, 2, or 4 multiply with the K1, the duration of loading multiply with K2, load sharing system, and multiply with K8. And this K8 is determined using the formula or table 10. So the second case is member subjected to axial compression and bending. So before we discuss further, we go back to this case A. So this member subjected to axial compression only when this loading, so this P, the location of the load is exactly at the centroid of column. Okay, so here is the centroid of column. Okay, so here is the load. Okay, so the P, the load, is exactly the point. The P is exactly located at the centroid of column. But however, for the actual cases out there, it is impossible to get case 1 where the P is exactly at centroid column centroid. Thus, this is the case number 2. So this case number 2 is member subjected to axial compression and bending. So when this load, okay, this is the for case 1. Okay, this is the case 1. Okay, only compression member where moment is equal to 0. Okay, once this loading, when this loading is located far from any direction of the centroid, from any direction, for let's say this loading is located at certain distance from X. Okay, so there is distance from this point to this point, meaning there is a moment where P multiply with distance here, then we get moment in X axis. So the moment is calculated using P multiply with EY. EY is the eccentricity, where the eccentricity is the distance from the load location. This is the P. Okay, load location to the X axis, because here is 0. Okay, so start 0, 1, 2, 3, 4, 5. So the distance is counted. Okay, so this is member subject to eccentric loading, where the P is at the center at Y direction, but not in the sector for X direction. Okay, so the next one is the eccentric loading is located at this point. So this is P. Okay, so this is the front view. Okay, this is the straight line. Okay, so we applied P here, and this P, this loading, is when we do the cross section here, and we can see the loading is located at this point. Okay, it is located on the x-axis, but far from the y-axis. So here is the eccentricity y. Okay, eccentricity y. Sorry, x. Sorry, in x. Okay, in x direction. Okay, in x direction. Okay, so meaning once there is direction and loading, so it can induce moment. Okay, so moment is at this situation is moment in y direction. Okay, and it is equal to p multiplied with the eccentricity at x direction. Okay, next is where the loading, this loading is located out of the centroid in x and y axis. So it is located here. So we have distance here at x distance and also here y distance. So in this case, there are two moments, okay, due to the rotation in x direction and also rotation at y direction. Okay, so this is for case B, where member subjected to axial compression and bending. For this case, we refer to clause 12.6, okay, and this equation is given in this clause. Okay, and this equation is used only for combination of axial compression and bending. Okay, so first, and also this equation is for members which are restrained at both ends in position but not in direction. Okay, meaning it is pin ends. Okay, so where and this is the member which are restrained at both ends in position but not in direction. Okay, and this member is subject to bending and axial compression. Okay, so this is based on this situation and should be proportion that. Okay, so must satisfy this condition. Okay, so this formula must be less or equal to 1. So where the first one, by using this equation, first you need to calculate this one. So this is the applied bending stress, where the applied bending stress is equal to moment divided by section modulus. So this moment is from the actual loading. Okay, so this is due to that's actual loading will cause bending. Okay, so Z is BH power of 2 divided by 6. Okay, so next is to calculate the permissible bending stress, where our permissible bending stress is bending parallel to grain. Okay, this is bending parallel to grain from table 1, 2 or 4 multiply with K1 duration of loading, multiply with the K2 load sharing system, multiply with the form factor and multiply with the depth factor K6 and also K5. So K1, K2, K5 and K6, please refer to beam design video. Okay, next is the applied compression stress. So this is the applied compression stress. So applied compression stress is calculated using compression loading, the axial load divided by cross-sectional area, okay, divided by A. So next is the permissible compression stress, where permissible compression stress is equal to compression parallel to grain, and this value is determined by using table 1, 2 or 4 multiply with the K1, K2 and K8. K8 can be calculated using formula as stated in Appendix D or using table 10. Okay, so next is the Euler critical stress. So permissible compression stress is this one, okay? So Euler critical stress. So this Euler critical stress is equal to pi power of 2 multiplied with the E, where in this case we use E minimum divided by Slenderness Ratio power of 2. Okay, so this is the Euler critical stress. So to solve this equation, you need to calculate each of these value first, then you combine all these value, substitute into this big equation. Later you need to check with 1, so it must meet this checking, okay, this verification. It must less or equal to 1. So this is member subjected to axial compression and bending. Example 5.4, column. Okay, so a nyatuh timber column with standard grade at 19% of moisture content is 4 meter in height. So the column is restrained at both ends in position but not in direction. Determine an appropriate size of rectangular cross-section column so that the actual long-term load of the column is more than 25 km. B. Check that the column is adequate to resist long-term axial load of 12 kN and a bending moment of 0.8 kN about its x-axis. So, in this example, given the species type, so this is species type, so to get the stresses, okay, we refer to table 1 or table 2. Okay, table 1 or table 2 in Malaysia Standard 544. Next, we limited the information to standard grade at 19%, meaning it is dry. So when it is dry, then we refer to table 2. It is confirmed table 2. Okay, and the actual length is equal to 4 meter L. This is L. And the column is restrained at both ends in position but not in direction, meaning this is the pin column. Okay, where our L E equal to 1.0 L. First is the case A, where you need to propose a rectangular cross-sectional, okay, rectangular cross-sectional column for the Azure long term, meaning this is K1, okay, our K1 is equal to 1, okay. So if you refer to table 5, MS544, for the value for K1 for the long-term load is equal to 1. And the maximum load, this P, okay, the maximum P is 25 kilonewton. It cannot exceed 25. Sorry. Okay, sorry. It must more than 25. So this 25 is the minimum value for P. Okay, let's look solution for the case A. So for the geometrical properties, so the length is equal to 4 and our effective length is 1.0 L. Okay, 4. And try size 100 multiply with 150. So this is the nominal size. Okay, so this is nominal size. So this nominal size, you can refer either from table. This is the case for the dry timber. So you need to refer to table 3B or table B3B. Okay, for the sawn timber at dry condition, or table B4 for the dressed sawn timber. Okay, so so in this example, it use dressed sawn timber. So refer to the table B4, dressed sawn timber. The minimum size is 90 millimeter for the width of section, and the depth of section is equal to 140. So this is the table 4. Okay, table 4, and here is our size, our nominal size, and here is the minimum size. Okay, so cross-sectional area based on this minimum size is 12,600 millimeter square. So B multiply with H, okay, 90 multiply with 140, and second moment of area is 20.58, okay, 10 power of 6 millimeter power of 4, where our IXX here is BH power of 3 divided by 12. So for this case, for the I direction, okay, this is our X, okay, and here is our, this is the Y axis, okay, Y axis. So this is X, so this is the B, and here is the H, okay, H. So this B, so for the IXX, okay, in the for the IXX in the X direction, so this is X, so this is the B, okay, this is the B. So meanwhile for the IYY, so similar with this equation, BH power of 3 divided by 12, where for this case, okay, so this is X, here is Y. So this is our Y axis, and the B is taken as 140. Okay, so this is the B for the Y axis. So this is how we read the second moment of area for the X and Y axis for column. So in column design, you need to calculate second moment of area for both direction, X and Y axis, and later we will select the least value, okay, the smaller value to in further design calculation. Okay, next is the radius of gyration. Our radius of gyration is 90 divided by square root of 12 equal to 26, where our B is the least dimension, and the section modulus is 294,000 millimeter power of 3. Our Z is BH power of 2 divided by 12. Okay, divided by 12. So this is the slenderness ratio. So our slenderness ratio is 4 divided by 26. Okay, 4000 divided by 26. Well, our 26 comes from this equation. Okay, and the effective length is equal to 4 meter. Okay, so thus we check our slenderness ratio is 153.85, which is less than 180, thus is satisfactory. Okay, all right. So the grid stresses. So for the grid stresses, based on table 2, okay, grid stresses is from table 2 because it is this timber having moisture content equal to 19%, meaning it is dry condition, dry timber, using the dry timber stress. Okay, so these stresses for the dry timber is referring to table 2. So first we take out the value for the under the nyato species. Okay, under the nyato. Okay, we select 12.3 for the bending stress parallel to grain. Next is the compression stress parallel to grain is equal to 11.4, and our E minimum is equal to 8,700. And this is table 2. Okay, here is nyato. Our bending parallel to grain for the standard group standard is 12.3, and our compression parallel to grain under the standard grade is 11.4, and we select minimum modulus of elasticity, which is 8,700. Next is the K factor. Okay, the K factor. So we need to know the K1, K2, K5, K6, and also K8. So K1 is from table 5. For the long term, K1 is equal to 1.0. No load sharing system, not mentioned in the equation. So K2 is equal to 1.0. Our cross-section shape is the rectangular section, thus our K5 is equal to 1.0. And the K6 is less than 300 mm depth. Okay, so our H is 150, which is less than 300 millimeter. So thus our K6 is equal to 1, and K8 is unknown and need to calculate. You need to calculate based on the equation in Appendix D or Table 10. So let's look Table 10 and also equation. So this is Table 10, Method 1 using Table 10. So if you still remember, so we have this column and also this column. Okay. So first we calculate this value and we get 763.16. Okay, 763.16. Next, we calculate the value of slenderness ratio. So slenderness ratio as calculated earlier is equal to 153.85. Please take note here that we use the I gradation in Y direction. Okay. So 153.85. So if you look at this table, so this is the calculated Young modulus divided by compression parallel to grain. Okay, and this is the value for the slenderness ratio. So it is in between 140 and also 160, and this value is in between 700 and 800. Thus our K8 is, the value of K8 is somewhere around this number. Okay, so you need to do the interpolation. Okay, it is here. Okay, somewhere here. Okay, so interpolation. So we extract this value. Okay, this is the extracted table. Okay, so the first interpolation is at this, okay, this column, okay, at this column. So we want to know how much value here, okay, between here and here is how much value. So the first one is, for the first interpolation is to get value in between 0.195 and also 0.154. Okay, so we take out this value. So at 700, okay, so this value is from 140 to 160. So here is 140. We have here is 153.85, and here is 160. Okay, for the 140, the value is 0.195. Okay, so and it goes down to 160, and the K value for 160 is 145, and at 0.153.85 the K is equal to X. So you need to calculate this X. Okay, so this X, finally we get X1 equal to 0.167. So 0.167. Okay, so next at 800. So at 800, so similar with this concept, okay, so we take out this, we draw one line. Here is 140, okay, here is 153.85, and here was 160, and our first K at 140 is 0.217, this value, and our 160, the K value is equal to 0.172. Okay, draw the straight line. This is the straight line. Okay, so our X2 is at this point. Okay, so do the interpolation, do the calculation, then finally we get the X2 equal to 0.185. Okay, 0.185. Okay, so this is in this direction. So how about in this direction? So between 0.175 and 0.185, between this value, so how much is the actual K8 based on 763.16? So we use the similar concept. Okay, so we have here, okay, under this column 153.85 at 700 is equal to 0.167, and at 800 is the K8 is 0.185. So how much K value at 700? 763.16. okay, 763.16. how much? So we use the same concept here. Okay, so here is 700. Okay, here is 763.16. okay, here is 800. So our 700 value K8 at 700 under 153.85 is equal to 0.167. Meanwhile, at 800, the K8 is equal to 0.185. We draw the straight line, and this is our K8, the actual K8. So you solve this equation. Okay, determine the K8. Finally, our K8 is equal to 0.178. Okay, 0.178. So this 0.178 is using method 1, table 10. And when we double check with the methods 2 equation in appendix D, we get the K8 equal to 0.77. Okay. So it is verified. So in later in the design, you can use either equation or table 10. Okay. So then start solving the case A. Okay, so we start solving the case A. So determine the appropriate size of rectangular cross section. Okay, so that the actual long-term load of the column is more than 25 kilonewton. Okay, so we need to verify that our stress actual compression stress, okay, must be less or equal to permissible compressive stress. Okay, so this is the permissible compressive stress. So it must meet this condition. So this actual permissible stress is the P over A, and our permissible compressive stress is equal to compression parallel to grain multiply with the K1, multiply with the K2, and multiply with K8. So we select this equation because our lambda is more than 5. Okay, lambda is more than 5. So we have this value. We have this is known, known, and known. And finally, in this A problem, we need to identify A. We only need to identify A. Okay, so finally we get our A is equal to our, okay, after you calculate A, okay, calculate A, so finally we get A equal to certain value, and later we refer to table B4 because this is the Gyration timber case. Okay, refer to table 4 and you select A slightly larger than this calculated A, and that is the proposed nominal size. Okay, so this is one way to determine the appropriate size of rectangular cross section. The second way to solve this problem by using the same concept. Okay, so this is the verification. Our stress, actual stress, compression stress must be less than permissible compressive stress. Okay, so in this case, you need to determine this P. Okay, so this is the second way to solve this problem. So this second way is shown as here. Okay, so this solution based on this second equation. Okay, so A is known as 12,600. So we know this value K1, K2 up to K8. Thus we select the P. Okay. We bring forward A into the right side, and the P is equal to 25.58 kilonewton. Thus it is verified that using the cross-sectional area 12,600, the P is more than 25 kilonewton. Thus, based on the 12,600, refer to table B4 and we select the size slightly larger than 12,600. And finally, in this example, it is selected, the selected size is 100 millimeter multiplied with 150 millimeter timber. So, okay, so meaning using these B cases, okay, the earlier proposed size 100 multiplied with 150 millimeter is adequate. Okay, it is okay. All right. So to solve this problem, there are two ways. The first one, either you select again the A. The second one is based on the loading. You get the loading. You check the capacity of this loading. Okay. Based on this area comes from the 100 multiplied with 150. So that the maximum, the load for this case is 25.58. Thus the earlier proposed size is adequate. So another method is if the size is not given, okay, so you can determine the A using P equal to 25. Okay, so P equal to 25. So from this A value, you refer to table before and you select the slightly larger number of A, okay, compared to the calculated A. Okay, so later you need to check again the P capacity. So this is solving A. So next is check that the column is adequate to resist long-term axial load and bending moment. So this is the combination of the axial load and also bending moment. So you need to use equation in 12.6. Malaysian Standard 544. Okay, this is the solution for B. Okay, we know that our axial load is 12 kilonewton and the applied bending moment is 0.8. Okay, so our compression bending stress. Okay, so if we refer to this case, first you need to calculate the compression and bending stress. Okay, so our applied compression stress is equal to P over A. So it is equal to 0.95 Newton per millimeter square. So this is our first calculation. The second calculation is permissible compressive stress is equal to the compression parallel to gray multiplied with the K1, K2 and K8. So it is equal to 2.03 Newton per millimeter square. So this is satisfied. Okay, so this is satisfied. For the combination of long-term axial loading and bending moment, you need to check based on the equation in 12.6 and also the case for the long-term axial load only. So this is similar with the cases long-term axial load only. So we bring this equation, okay, this value 2.03 and 0.95 to equation 12. As stated in the clause 12.6 Malaysian Standard 544. Okay. So next we calculate the applied bending stress. So this is for this case is this equation 1, 2 is to satisfy the resist axial term loading for the axial load, and next we check for the bending moment. Okay, so this is the bending moment. Applied bending stress is equal to M moment divided by Z, and this is the equation for moment. Okay, applied bending stress where our moment is equal to given 0.8 and our ZZ is 294. 000 and our applied bending stress is equal to 2.72 Newton per millimeter square. And then the fourth calculation is the permissible bending stress equal to 12.3 by substitute all these value determined earlier, okay, into this equation, and then we check our bending stress is satisfied. Okay, so this is value for bending stress. Okay, so bending case. So next we bring this value, and this value into equation as stated in 12.6. Malaysian Standard 544. Okay, in this equation, you need to calculate this Euler critical stress, okay, based on the using E minimum. Okay, so finally we get the value for the Euler critical stress is equal to 1.15, and we substitute all these calculated value 1, 2, 3, 4, and 5 into this equation. Okay, substitute all calculated value into the equation, and we get 0.75, which is less than 1. Thus, this proposed 100 mm multiplied with the 150 mm is satisfactory. Okay. So next is example 5.5. So a column is loaded and supported as indicated. So this is the loading P. So the column is surface 150 multiplied with the 250 mm. So this is the nominal size, common grade. Okay, common grade. The species is Penaga and used at 16% maximum moisture content. So this is the, we need to use the dry stresses. So need to refer to table 2. The dry stresses is from table 2 because it is dry condition. Okay, and our species is Penaga, and also the grade is common. Okay, so the loading is combination of dead load, live load, and also the wind load. So here is the wind load. So determine the maximum allowable constraining load. So how much is the P, okay, that the column can adequately support. So the L is equal to 4.2 meter. Okay, so this is the solution. So this case is only the axial compression loading only, so no combination with the bending. Okay, so our column length is 4.2, our effective length is 0.85 multiplied with the L. Thus our effective length is equal to 3.57. Okay, so where our end here is fixed and the top here is a pin. Okay, it fixed in direction, sorry, it fixed in position but not in direction. Okay, so thus our effective length is equal to 0.85 L, and the proposed size, nominal size, is 150 multiplied with 250. And the surface reduction in this example is using table B2. Okay, table B2. So this is table B2. Okay, where our X, if more than 150, the maximum reduction by surfacing is 6 by reduce 6 millimeter. Or you can also use the 6% reduction, either one. Okay, either you use table B2 or 600% reduction. Okay, so if you use table B2, so all these 150 and 250 is minus 6 millimeter. But in this, in this example, it used 6% reduction. So this is the maximum value for the reduction percentage. So finally, we get the B minimum based on this 6% reduction, okay, is equal to 141 millimeter. And the H minimum due to the 6% reduction is equal to 235. So our minimum size is 141 multiplied with 235. The B, the width, and also the height. So this is the minimum size. And using this minimum size, we calculate the cross-sectional area, calculate the second moment of area both in X and also Y axis. So here is 141, here is 235. So this for the IXX. Okay, here is B, here is H. Okay, for the IYY, here is B, here is H. Okay, so where our here B H power of 3 divided by 12, here is B power of 3 H divided by 12. Okay, so next is the radius of gyration. Our radius of gyration is 40.70 by using the B is equal to the least dimension, and our section modulus BH power of 2 divided by Z is equal to 1.3 10 power of 6 millimeter power of 3. Okay. Next is checking the slenderness ratio. Our slenderness ratio is equal to 87.71. You substitute the L effective, then also the radius gyration, and our slenderness ratio is less than 180, so thus it is satisfied. Next is the grid stresses. Our grid stresses is from table K2, table 2, because our moisture content here is 16%, and the compression parallel to grain is 21.1 based on the Penaga species, and also common grid. Okay, so our E minimum is 15,800 Newton per millimeter square. And our K factor is equal to 1.5 because it is in this example the loading is short-term loading. So as mentioned here in example 5.5, the loading is combination of dead, impulse, and also wind. And based on this table 5, dead, impulse, and wind is short-term loading, and our K value is 1.5. And K2, no load sharing, is equal to 1, and you need to calculate KH. And based on the calculation, okay, equation in appendix D, okay, we finally get our KH is equal to 0.332. So where our value n here, so n here is the reduction factor equal to 1.5. Okay, this is 1.5. Our E yang modulus here is E minimum. Our radius of gyration here is as calculated here, 87.71. Our eccentricity factor, this is the eccentricity factor. Okay, this is our eccentricity factor, where the eccentricity factor is equal to 0.005 lambda multiplied with the slenderness ratio. So, and our compression stress here is equal to compression parallel to grain multiplied with the K1, and we get the KH is equal to 0.332, and we substitute all these value into this equation. So we know that the stress, the applied compression stress parallel to grain must be less or equal to permissible compression stress parallel to grain. So we know that we need to satisfy this situation, okay, this condition, okay, must be less. This is applied, okay. So we know that this P over A, okay, should be less or equal to compression stress parallel to grain from table, this is from table 2 multiply with the K1 multiply with the K2 and also KH. Okay, so the question is to determine the maximum load can be received by the column. So we need to determine P. So we know A, this is known and known value, And finally, we get our P is equal to 349.57 kilonewton. So this is example 5.5. Next is example 5.76, where the length of the column is not same. Okay, so the bottom column is having length, actual length 2,400, and the second column, okay, the first floor column is 1,800 millimeter. Okay, so the column is loaded and supported as shown in figure. So the column has a surface 150 multiplied with 250. So we do not have 250 size in table B3A, B3B, and also B4. Thus you need to reduce using table B2 or using the 6% surface reduction. So our grade is common grade, and the species is Penaga at 16% maximum moisture. So the information given is similar with the example 5.5. So we refer all the dry stresses from table 2. Okay, so the same cases, this is the short-term loading, and you need to determine the maximum allowable concentric load. Okay, so how much is the loading? Okay, for this column with different length. Okay, so this example 5.6 is similar with the 5.5. The difference is at the length. Okay, so here is there are two length, which is 2.4 and also 1.8 meter. Okay, so given the surface 150, this is the nominal size and this is the minimum size, and we already determined this modification factor, okay, from equation from example 5.6, and we add this additional value K5 and also K6. K5 is for rectangular shape and also K6. So when we need to use K5 and K6, or when we no need use K5 and K6 for the compression loading, to check the compression axial loading, you only need K1, K2 and K8. Meanwhile, if you need to check the due to the bending, okay, due to the bending, so you need to determine the K5 and K6, because equation to check the bending capacity, there is modification factor for K5 and also K6, and next you need to determine the K8. So there are two axes here, if you can see here. So this is the Y and this is the X. Okay, so this is loading. Okay, here is the fixed end. Okay, the fixed end, so it is cannot rotate in both position and also direction. Meanwhile, here is fixed at position but not in direction. So in Y direction, if you can see in this Y direction, so there is beam here, okay, that restrain the Y direction. So this is the X direction. So if this loading is applied on this column, it can cause two types of bending or slenderness bending. First one is in X direction. So this is the X direction. Sorry, so here is X, and our bending direction for X is at here direction. Okay, if you look from this view, so you can see this is the bending, okay, due to the load. Okay, due to the load. Okay, so where our L here is, LE here equal to 0.85 L. Okay, so meanwhile, for the y-axis here, so the buckling tends to buckle at this shape. So we have one here. You see, this is the first restraint, and this is the second restraint for due to the pin position. So it has two shape, okay, buckling shape. Okay, so like this. Okay, all right. So at the first floor here, from here to here, so the buckling is like this. Okay, so the first one here is pin. Here is pin, where it is restrained in position but not in direction. Thus our LE is equal to 1.0 L. And meanwhile, at the ground floor column here, the bottom column here we know that at this end position is fixed, where it is restrained in both direction and also position. Here is pin. Okay, thus this LE is equal to 0.85 L, similar with this, okay, at x direction. Okay, so this is our bending at x-axis, and this is bending at y-axis. Okay, so radius of gyration, both axes, IXX and also IYY. Okay, for the IXX is 69.28 and the IYY is 40.42. Okay, so this is our cross section for the IXX. Okay, so we know that here is our B, the proposed minimum side is 140, and the finish H is 240. Okay, and to determine the worst buckling condition, you need to check condition A, B, and also C based on this 0.85, 1, and also 0.85 for the y-axis column. Okay, so we check our first slenderness ratio for the case A is equal to 51.53. Okay, and for the B and C, we use the radius of gyration at Y. Okay, because we consider at y-axis here. Okay, so we got the case B is equal to 44.53 and case C is equal to 50.47. Okay, so this is our factor, okay, based on the end condition. And thus from these three values, we check that the critical slenderness ratio, the largest value is 51.53, and we will bring forward this value into the next stage. So next we determine the KH, okay, from equation. Okay, so from the appendix D, finally we got the KH equal to 0.647. Sorry, this is using, if I'm not mistaken, this is using table 10 because it's using interpolation. Okay, so from the first column for 497, and from the radius of gyration 51.53, then we do the interpolation, and finally the KH is equal to 0.647. And from this verification, we know that P over A must be less or equal to stress, compression stress parallel to grain multiply with the K1, K2, K5, K6 and K8. Okay, all right, so our permissible compressive stress is equal to 20.58, and our P, okay, finally we got our P is equal to 691 kilonewton. By substitute our A with 140 multiply with 240. So this is the maximum concentrated load that the column can adequately support. Okay, so example 5.7. So example 5.7 is using other shape other than rectangular. Okay, under the rectangular. So this is the round columns. Okay, for the round columns, if the round columns K5, okay, is equal to 1.15. Okay, where's my pen? 1.15. Okay, so when to use this K5 1.15 is the checking. You check the compression Azure load only. So the equation is K1 multiplied with K2 and also K8. So no need to multiply with the K5. But if you check the capacity, the bending capacity, okay, so you need to multiply K1, K2, K8 with the form factor K5 and also the depth factor. Okay, K6. Okay, so let's see example 5.7. So a 150 millimeter diameter lock. Okay, so this is the lock. Okay, 150 diameter. So it is round columns, 4 meter long. This is the actual length. Is used as a compression member in a foundation system. The member is considered to be pinned at top but fixed at the bottom. So meaning the L effective is equal to 0.85 multiplied with the actual length, which is 4 meter. So it is made of select grade compass. The species is compass and the grade is select, and it's not surface. Okay, so it is used in an environment with a high moisture content and normal duration. Okay, so if high moisture content, thus you need to determine the stresses from table 1. Okay, so table 1 is using the wet stresses because the moisture content is high. Okay, and determine the maximum concentrated load for the member. So determine P. Okay, so this is the solution. Given diameter 150, the actual length is 4000 millimeter, and our effective length is 0.85 multiplied with the 4000. Thus our effective length is 3.4 millimeter. Our compression stress parallel to grain from table 1 is 22.3. In table 1, you refer to the species compass and grade select. Okay, and our E minimum is 13,100 Newton per millimeter square, and for the normal loading is K1 is equal to 1. Our round area is pi d power of 2 divided by 4 is equal to area, the cross-sectional area for the round column is 17,671.46 millimeter square, and our moment of inertia is pi r power of 2 divided by 4. Thus our moment of inertia is this value, and we need to determine K because the question is to determine the P, and this foundation system receive only compression. Okay, compression load, meaning axial compression load. No mention about bending. So the foundation system is receiving the axial compression only. Thus, you need to check this P using permissible stress, compression stress parallel to grain multiply with the K1, K2 and K8 only. Okay, alright, so thus you need to determine the K8. So our K8 here is from table 10, we got 0.345. Later you can look at table 10 and do the interpolation based on 90.67 and also 587, and we get our K8 is equal to 0.345. And finally we do this from this relationship where from this checking where our actual compression stress perpendicular to gray must be less or equal to permissible compressive stress perpendicular to grain, where this value is P over A, okay, equal to this stress, wet stress. This is from table 1 multiply with the K1, K2 and also K8. Okay, so our K2 here is no load sharing system, so meaning our K2 here is 1. Thus you need to finally you calculate P by bring this A to the right side, and you get P is equal to 139.32 kilonewton. Okay, so this is example 5.7. Okay, to determine the maximum allowable constrained load, okay, when the cross section is round shape, okay, round shape. Okay, so this is exercise 1 column. Later you can do it and discuss with your team member. Okay, so you can discuss with me also if you have any question regarding this topic and also exercise 1. Okay, so that's all for chapter 5, timber part 2. Thank you.